Hello, and welcome to Coroutines Explained by Example Talk. The motivation for this talk is that, from what I've seen in software industry, coroutines is the most widespread and the least understood of the widespread features in programming languages. So in this talk, I'll attempt to explain how they implement various languages and what they mean at a fundamental level. So it's kind of an overview. You can ask your questions at Slido, and I should be able to sit on the other laptop, so you can ask questions anytime. So here is a brief and definitely incomplete history of coroutines. Everything I will mention is nothing new because coroutines were the first time mentioned by Melvin Conway in '58. Then there was explanation 63. It was implemented in Simula 67, and it was available in Scheme in 72. Then there are like 3 dots. I'm sure there are many more things that happened, but I wasn't around, and it's difficult now to research what happened. So, but I assume there are lots of things happening because by '93, John Reynolds felt like it's worth publishing a paper in which he described how coroutines were rediscovered like in 3 different ways over the years before '93. So even by '93, it was a very old topic. So then there was a period when there was not much going on, I guess, in '90s, and I assume the reason was that before '90s, most systems, you couldn't just get a thread, and so if you wanted concurrency, you had to use coroutines. Then in '90s, operating systems started using threads, and people kind of forgot about them. And then recently, there seems to be a renaissance of coroutines in various languages. Here is simplified history of 2000s. So in 2001, Python got a yield keyword. Later on, other features then, there was C#. Noticeably, JavaScript got async await and yield. And then there was Kotlin in 2017. Then LLVM got support. And this year, C++ 20 standard got coroutines. So next year or in the future, we'll expect C++. And also there is Project Loom for Java. So I assume in a couple of years, we'll have coroutines on JVM as well. So that's a short history. Why would you use coroutines? There are, I would say, 3 reasons. One is cooperative multitasking in a single-threaded environment. So, for example, JavaScript is single-threaded, but if you want concurrency, you have to do it. Another reason is to simplify your code. For example, generators or avoiding callback hell. And yet another reason is performance, because coroutines are cheaper than threads. So if you need high level of concurrency, you will benefit from using coroutines rather than lots of threads. And there is also a hard limit on operating system, how many threads you can have because of memory issues. So there is no standard definition of coroutines. Here is a simple explanation. So coroutine is a function which can suspend its execution and can be resumed from suspension point, keeping its original arguments and local variables. So it will be more clear, I hope, later. So here is the agenda. We will look at 3 flavors of coroutines as threads, yield, async, await, and coroutines with current continuation, which is called CC, and then callback hell and coroutines versus promises. So let's start with coroutines as threads. So I'll use Lua as a programming language to show how coroutines are used as threads. If you're not familiar with Lua, it's pretty much like JavaScript for C++ programs. So it's a language which integrates with native languages and easy to program in. So for explaining visually what's going on, I'll use this notation I made up. So here on the left, it's a main function, and imagine there are instructions top to bottom. And on the right, there is some sub-function. So arrow represents what CPU is doing. So we have entry point into main, then we do some work and call a function. Then we execute the body of the whole function, jump back to where we were in the main function, then we finish main and return. So that's like the normal call of sub-function. Here is the same thing in Lua. So we have this whole program here. So it prints hello. So firstly, we define subroutine. Then we print hello, we call subroutine and print Lua. So if I run this, it prints hello from Lua over here. So that's what we just saw on the diagram. Now, what if we call coroutine? So we have main function, we call it, we go into coroutine, and then at some point in coroutine, we reach a suspension point, which means, in some abstract way, save stack and current instruction pointer somewhere on heap. That's like totally an abstract way to think about it, not necessarily what's going on. After this, coroutine jumps back into main, at some point, we can again look at the stack and instruction pointer, restore them, jump back into the middle of coroutine. Then we execute a bit more code, suspend again, and then jump back into main, finish main. And as you can see here, we didn't even finish running all the code in coroutine. So here is these 2 points, suspension points, and here is the same code in Lua. So here we define we call library function called coroutine create. It takes a lambda, this whole thing, and then it's all saved into a variable called c. Then in main we print 1, we resume coroutine, so it prints to 2. Then it prints 3, then 4, and then 5, and we never see the monkey at the end of the coroutine, so it kind of matches what we just saw on the diagram. Of course, we can kind of resume again, then we will see the monkey here. Yeah. It's worth noticing that we cannot yield from main here, so it's not exactly it's not a symmetric relationship here. So similar to threads in Lua, you can have status of coroutines, they have statuses. So here it's pretty much the same setup. If we run this, we can see that at point 1, coroutine is suspended, and point 2, it's running, and so on. And at point 5, when we finished executing the body, the coroutine is in state called dead. So this is kind of mimicking states of threads. Also, in Lua, you can send and receive values when you yield in or resume in content. So running this example, we can see that main initially sends, which resumes coroutine and sends 1, so C receives 1. Then when coroutine yields control, main function over here, it returns variable m, and so main receives 2. So when you switch context between coroutines, you can also pass values between them. If you kind of ignore the same diagram we've seen before, if you ignore entry points into main, you can actually think about it as a symmetric picture. So you can see this could be like 2 coroutines, right? It doesn't have to be a main function. And similarly, you can reproduce this behavior in Lua, so you can create 2 coroutines and they can yield and resume each other. So this again prints 1, 2, 3, 4, 5. You can also, there is another thing which makes coroutines in Lua behave like threads, is that they're stackful. So if you think on the left half, or the main function is one thread, and the other coroutine and subfunction, that's another thread. So we can call from main coroutine, and then if we suspend inside subfunction, then control flow jumps all the way back to main. So it's not just a normal return to its parent function, it jumps all the way back to main. So in this way, it's pretty much like context switch between 2 threads. So then later on, we can again jump back into the middle of subfunction, and then we can finish subfunction, finish coroutine, and go back to main. This is like a non-local return. So here is the code when we create coroutine, and inside coroutine, we call this subfunction. So when we run this, prints 1, 2, 3, 4, 5, 6, 7. And the interesting thing is that after yielding here, we jump all the way back to main function, to 4. And we can even see it in the stack trace. If we look at this, it remembers it was on line 10, and before it was on line 16, so it's like an actual stack, like you would have stack on a thread. So this is the distinction between stackful and stackless coroutines. So stackful means that you can actually jump like this from some function. Stackless means you cannot do it. For example, in JavaScript, you cannot do it. There is also, it's also worth noting here is that coroutines don't necessarily imply parallelism. So they're all about concurrency. You can use them from one thread or multiple threads. That's a kind of separate concern. All we've been doing here, because Lua is also single thread, was a single thread simulating multiple threads behavior. And you might want to do it for various reasons, because maybe, for example, you don't want to have multiple threads because single thread simplifies lots of things. So there are related terms to using coroutines as threads, as fibers, green threads, as threads were in Java before they were mapped to native threads. Then there are proto-threads and Go routines. There is like, it's a bit of a fuzzy term. For example, Go routines, they're kind of like coroutines, but you don't control when you switch between them. So like Go decides it for you. And there is no clear-cut definition what is what can be considered coroutine, what is not. So here is the summary of coroutines as threads. So it's basically kind of two threads passing control between each other, and you can decide when you can yield control. So there was a question about what the difference between goroutines and coroutines. I hope I answered it. So let's move on to like the most widespread coroutines implementation is yield, async, await. And I'll use JavaScript as an example because it's a dynamic language, so we don't need to think too much about types, and I hope its syntax is understandable enough. So let's start with yield, keyword, or generators, and they're quite similar to coroutines as threads, but they have a different purpose. The way I think about it is like design patterns. So fundamentally, design patterns, they're all about like virtual functions. So this is a similar things, like just different purpose. So generators usually is for doing lazy calculation, and they're usually used for doing lazy calculations. They can always be rewritten as iterators, but it can be more convenient to write them a different way. So to compare with previous coroutines as threads, so this was main calling coroutine, and this is a generator. So it's like identical thing. So main function calls the generator. At some point generator yields control and sends value back. To show this in JavaScript, we can do create generator, which will yield dog, pig, and a monkey. And we save this generator in variable C. In JavaScript, you have to use star to tell the language that it's going to be a generator. So then we can call next on the generator, and we print out the value. So if I run this, similar to previous example, it prints dog and a pig. And we need to add one more thing to print monkey. Also, with generators, you can not only receive values, you can also send values to generators. So here, when we call next on the generator, we send values. So initially, we send A is A, but in JavaScript, it's lost. But the next value is received. So if we run this, we can see in the main function, we received the dog here. Then this whole yield was evaluated into, it was just, it was validated to B, I think. And then if we do, let's say, C, we'll see we get C back here and a monkey. Similar to threads, as you can see, this is very similar to what we've seen just before. So it's basically, again, context switching. You could yield nothing and basically simulate this coroutines as threads. So here it prints, again, 1, 2, 3, 4, 5. So it's exactly what we saw with Loom. And generators in JavaScript and many other generators, they're similar to threads again, they have state. So here we can see that after we yield it twice, the generator goes into the state, which is called done is true. So it's kind of similar to the state of coroutines in Lua. Unlike Lua, though, they are stackless, so we cannot really do yield from a nested function. So for example, here we have generator, which has an array of 1 to 3, and we do for each and pass an anonymous function. An anonymous function is still a subfunction, so we cannot yield from here, so it's just like incorrect code in JavaScript. There is an obvious workaround for this to just use a built-in for loop, and this thing will work, and this generator yields 1 to 3. And the reason it works is simply because JavaScript knows about how to handle for loops with coroutines, so it's just hard-coded into language that this construct can be used with coroutines. So it's a special knowledge. Similarly, JavaScript knows how to handle try-catches with yields. So in this example, we'll throw something, then we catch it, and we will yield it. However, this yield is not a return. So if I run this, you can see it sends back a rocket plus explosion. So this is what we get here. And we need to yield again to run finally. So if I remove the comment out this line, we don't get finally. So this is not like return. If this was a return, finally would be run, right? So yield is not exactly like finally, and there is built-in knowledge about this. In other ways, generators, they can be used in constructs like while true. So here's how we could calculate factorial. So basically loop forever and yield result, then increment n and multiply result by n. So this like a way to calculate factorial. So like slightly weird way to write a function. It could be rewritten with iterators, but it's just sometimes much easier to write it in this way. And we can extend this example with functionality to skip few results before returning them. So say if we don't skip, then we yield results. Otherwise, we kind of decrement the counter of skipping. So we can say next, and then we pass next 10. So we skip 10 values of factorial, and we get to a larger value. So this is why it can be useful for sending results to generator. The actual example would be if you, let's say, lazily reading from a database, but at some point you want to cancel your reading. So you could send a value to generator to cancel reading. And it all looks kind of magical, so that like JavaScript can figure out how to yield from a while true loop. But in reality, it's always transformed to a finite state machine. So here is the code generated by Babel.js. So it's this code. So this code was from JavaScript version, which supports generators, and this is JavaScript code, which can be run in previous versions. So it's like code with the same functionality, but translated for all the JavaScripts. And you can see this bit of const factorial and next 10, it's exactly the same. So these 3 lines stayed the same. And then our function definition is slightly different now. So essentially, we're kind of defining an object here with these fields and result and skip, and these were local variables, right? Then we enter a state machine, and like details are not that important here. The important thing is like we go into the state machine with the state 0, and we initialize variables. So this is similar to what we had with local variables, 0, 1, 0. Then we fall through, and then we do some comparison. This is going to be false. And then we say if skip, then we jump to a state 10. And this is the state 10, and this skip -1. So basically it says go to here and do -1, and so on. So the whole code is taken apart into a state machine. And this is how it actually works. So here is the summary of generators. So it's pretty much like switching between threads, but you send in value back at yielding points. So now let's move on to async await, which is probably the most complicated implementation for coroutines. So again, they have a similar example. We have main function, which calls async function. And at some point in async function, we can do a synchronous call, which will return us some promise. For example, we make a call to remote server. And we can await on this call. And what it means is that environment will chain the rest of the current async function to this promise, and then it will immediately go back to the main function. From this point of view, await is quite misleading keyword, because usually when you think about code, you reason as a CPU, what I'm going to do. And actually CPU, when you do await, it doesn't wait, it jumps out of the function. It's awaiting if you think of it as a function itself. So CPU is basically don't await, it jumps back and finishes the main function. Overall, it also returns a promise of when the whole async function will complete. So sometime later, some other thread or the same thread fulfills the promise and executes the chained call and jumps back into async function. Then again, you can do another async call, you create another promise and chain the other parts of the function to be executed when promise is fulfilled. And so this is what happens, it's fulfilled later, and we jump, and we jump out of the whole async function and execute the overall promise. This is a bit convoluted, but the whole idea here is kind of similar to this, like red points. We basically save the current point of execution and the rest of the function, chaining it to promise. So here is some JavaScript code. What we do here, we have two promises, 1 and 2. What this promise will do, as soon as we create it, it will start a timeout of 2 seconds, and in 2 seconds, this whole promise will resolve to a dog. This simulating receiving a message from external system. And the second promise will return a pig after 5 seconds. And here we create a syn function, which awaits for the first promise and prints the results, like what we received, like a dog here. Then it does the same for the pig. And at the very end, when we call async function here, C, then we chain the thing to print the result, which will be dog plus pig here. So if I run this, as you can see, we finished the main straight away. Then 2 seconds later, we got a dog. Then we got a pig, and the results changed. So this is what I was showing before, is that await jumps out of async function straight away. So in a way, it's not really await. It's not really waiting for anything. So this is misleading compared to other function names. Also, as soon as you name function async, the whole function actually returns a promise. So this dog and pig, they were strings, but after returning from function, they become a promise, wrapped as a promise. So that was the previous picture, but now you can think of those promises as another overall promises. So it's basically, it could be another await on another async function. So this is all composable, this whole idea of promises. So here it's like pretty much the same thing, except that now in coroutine we await not on promises, but we await on async functions, which await on promises and so on. So this is all basically a composite pattern. So if I run this, this should work the same way. So end of main, and then after here, like we wait for 7 seconds because we wait for the whole function. We wait for C. Yeah. So similar to generators like JavaScript and other languages using async wait, they also integrate with all language constructs. For example, try catch. The details here not important. Similar to generator, you can just use them together. And again, just like generators, this whole thing is converted into state machine, so there is no actual magic. You can also see that async is converted to generator, and then the whole thing is converted to finished state machine. Again, details not important, it's just I'm trying to say there is nothing magical about it, it's just some transformations. And so this is the summary of async await. So await on promise changes the rest of the function and returns to the function it was called from. So let's move on to call CC, or let's call with current continuation. And for this, I will use examples from Scheme. The reason is that I think it was the first language which implemented it. At least it was quite influential. For example, looking at Boost library or some other libraries, you can find functions called call CC, and they just imply that you know what it means. So to start with, let's look at what continuation means. And it's also a fuzzy term. People can mean different things. For example, it can be just meant simply as a callback passed into a function. It can also mean, in a more computer sciencey way, a function representing the rest of the program. Or it can be representation of continuation in a particular language. For example, in Ruby, there is class continuation. Or it can mean that compiler environment implements continuations. So what I will mean more like the first two definitions. And there is also continuation passing style, also called as CPS. So to give an example of continuation passing style, here is hello world in Scheme. So if I run this, as you can guess, it prints hello world. This is the main function, and these are two functions taking arguments, hello and world. So here's the same thing in CPS. So instead of built-in display function, we have to define our own. It takes a message and continuation, where it means the rest of the program. So now we print hello world and pass an anonymous function, this lambda, which will do another call to print world, and it takes another empty lambda to finish the program. So that's continuation hello world in CPS. Right, we can do factorial, so this is normal factorial, where if n is 0, this is 1. Otherwise, we multiply n by factorial of n minus 1. So it's not the most efficient, but it should work, like 120. So if we rewrite it in CPS style, it will look something like this. So when we call it, we pass 5, and then we pass what we're going to do when factorial finished, and that's display result. Right, and then in factorial, it's not so trivial, but the easy way to think about is kind of is return. Not always obvious, but so there are certain benefits to using continuation passing style. I'm not going to go into details, but basically all these transformations that I showed, they're kind of convoluted, even in this trivial example. So call CC basically lets you do it way more easily. So here is an example of call CC. So here's again main function, we print 1, and then we use print, and we do call CC with current continuation. This is like built-in function in Scheme, and we can pass it anonymous lambda, and this lambda takes a continuation, which literally means the rest of the program here. So inside the call CC will immediately execute the lambda, so it will print 1, then it will print 2. And then we call continuation, which means the rest of the program. So this whole expression will be evaluated to 3, and then the program will continue executing. So it will print 1, 2, 3, 4, as you can guess. This example, like you can say this was, and we'll never see the monkey, right? But you can think about it as return here. So this was just the return to run the rest of the program. It's also interesting that the rest of the program means everything starting from current expression, not a statement or something like that. So here is a bit more convoluted example, which maybe shows better what call CC is doing. So let's say we have a global counter, it starts with 0. Then we do a print of this expression, and inside expression we do call CC, and we get continuation, which we just save into another global variable. So now we just saved the continuation, and we call saved continuation to like 100. So this whole expression at this point will be 100, we should print 200. Right? Then we get to the counter, counter is less than 3, so we'll increment the counter here. We print a rocket, and then we call saved continuation, which is the same saved continuation from here. And basically it means, again, this whole expression will be evaluated to the current count, and count will be 1, so this should be like this, 101. And we, again, like jumped to this point of execution. So if I run this, you can see it prints 200, then it prints the rocket, then it uses current counter and jumps to this position, and it does it several times. So it's a bit like a structured goto. So not something you can do with other constraints. So here is a schematic example of what we've seen. So in main function we have call CC, and in some way you can think of it again as just saving stack and instruction point somewhere in memory. Then we pass in continuation, and inside continuation we can jump back into main, and then at some point in main we still have access to this stack instruction point, and we can just loop like this. So the reason I mentioned this is that this is how also like the way Coroutines implemented Kotlin, they're done in a way similar like this, inspired by Scheme, I guess. And this is, I think, the most fundamental way of implementing continuations, because using this you can implement all the previous examples. So here is not a full, but like very simple implementation of yield and resume using call CC. I'm not going to go into details because it's kind of involved, but this is like one of the most fundamental ways to use continuations. It's also interesting that continuations are not just a compiler hack, as you've seen for JavaScript, which can say, oh, just a transformation to state machine. And there is this paper about a definition interpreters of higher programming. It's quite an old paper, and I heard about it from Phil Wadler at a meetup. So that's, if you're interested, you can read the paper or watch the video from the meetup to see what exactly it means. So now we can look at callback how. For example, we have blocking data source, and here it will take an array of 1, 2, and 3. And blocking data source is just an object. You can see here, again, it's JavaScript. It's an object with function blocking read, which will just remove the first element from the array. So if we run this, it will print 1, 2, 3, 1, 2, 3, done. So this is like a simple synchronous data source. Each of these calls are blocking. Now, what if we define a synchronous data source? So here we define, again, data source and pass in an array of 1 to 3. Then this object will have a function called async read, which will take a callback and will call the callback with the first element from the array after some delay, let's say 10, or 0 is the same, so let's say 10. Then we can use this data source in this way. And as you can see, this soon becomes nested, and this is the callback hell, when if all your calls require callbacks, then it's like you have to have a very nested structure in the code. And it's also way more verbose compared to this. You can see it's not that nice. There is like, so if I run this, it still prints, well, prints done 1, 2, 3, because now everything is asynchronous. There is an obvious solution to this, like well known, to use promises. So here we again have the same asynchronous data source, but now instead of reading directly from data source, we can define a function, read promise from async data source. And here we can create a promise, and inside the promise, we just immediately start reading from data source, that's the call, and then we'll pass as a callback resolution of the current promise. So as soon as we receive callback from our synchronous data source, it will complete our promise. So at this point, this thing becomes a promise, then we get a result here, then we can do another read, and so on. So at least, as you can see, it's still a bit more nested than the original example, but at least it doesn't go right forever. Right? So that's like the next best thing you could do. So again, it prints done 1, 2, 3. And it's kind of verbose. So what you could do with coroutines is basically use await on the same function. So here, what has changed is that we defined a function called coroutine, marked it as async, so JavaScript knows how to transform it, and then we can await on it, and our code basically back to what it was with blocking reads. So if I run this, again, it prints done 1, 2, 3. So it's equivalent to working with promises. So here, the whole trick here is that you can transform any API with callbacks into flattened API using coroutines, or like async await in particular. And the whole trick is that you can finish promises using triggered callbacks. There is an interesting talk by Eric Myers, contravariance is the dual of covariance, implies iterable the dual of observable, like obvious, right? And here's like my quick explanation, spoiler alert. I think the main gist of the talk is that iterator and observable, if they designed in the right way, they are kind of symmetric. For example, here we have iterator and it has a function called current. And the signature of the type of this function is like takes unit and returns t or some value. And this is basically a blocking call, right? For observer, you have the opposite situation. You don't get anything back. You create a function which returns t, but receives t, but returns nothing. So this is asynchronous. And similarly, when you move to next, you have options. You have next value, you don't have next value, or something went wrong. And this is what you would get in observer. You complete it, or you get some error. And schematically, you can say the first example is blocking. You get from your type signature of your function is unit to something that's blocking. Otherwise, you'll have a synchronous function which receives something and doesn't really return anything. And so with coroutines, you can kind of go way back. So this is what I was trying to show, when you can go from nested, when you can go from API with callbacks to normal API. So to some extent, this is possible to do it with coroutines. There are some caveats to it, but that's like in general, the idea. So now, why wouldn't you use, for example, promises all the way? So here is again the example with sequential read from async data source. So again, we have async data source of 1, 2, 3, 4, 5, and then we iterate and read 3 elements from here. So this is an example with coroutines. So we do await here. So if I run this, obviously it prints 1, 2, 3. So guess how you would do it with promises. So here is the actual answer. You might think you could do it, for example, like do the new promise, and then just read here, like this. No. Yeah, good, like read promise. Why not just do that, right? And then if we run it, anyway, so it's not so simple. The problem is that you cannot just read things sequentially. Actually, it should have been like this, right? We read promise, and we then chain then, and then we can do console log here, right? You might think that's the answer, but the problem here is that because everything is asynchronous, you cannot guarantee that some promise won't be finished before the other one. So we cannot do console log here. So basically, we need to chain promises as like a fold. We need to fold them all and then execute to make sure that they're all sequential here. So we need to have an empty promise, then we do this. This is like a trivial example. What if we do a bit more, something more complicated? We have a synchronous data source with 2 nulls, and then we have some values. Right? So now what we're trying to do, we try to read all the values while we're trying to retry until we get an actual value, but we also have retry attempt of less than 5. So while value is null and retry attempt is less than 5, we read from data source and then we print. So, and we increment retry attempt each time. So if we do this, we kind of read null, null, then we get a dog and we finished. So this is kind of retrying, let's say, from some other service which might be down and so on. So it's a simplified version of that. So what if we do it with promises? So here is an attempt, and it's straight away way more complicated, and actually it's incorrect. And the problem here is that the problem here is not exactly with promises, that in reality we're trying to translate imperative solution into functional world, and here is just difficult to translate it. And that's the problem with using promises, that they kind of push you into functional world straight away. And not all languages are designed for this very well. So I'm sure it might be very nice in Haskell for Haskell programmers, but languages like Java, for example, they're not necessarily perfect for this type of things. And here there is a good talk by Ron Pressler about, like, please stop polluting our imperative language with the pure concepts. So this is why you might not want to use promises all the way. So here's the quick summary. So again, why would you use coroutines? So again, it's a cooperative multitasking in a single-threaded environment. You again might want to have single-threaded environment because it solves lots of problems with concurrency. So just single thread is always simpler. Then you can simplify your code by using generators, or avoid callback hell, or just change API using async away to a similar construct. And also, the other reason is performance, when you need high level of concurrency. So again, this is overview of this is coroutines as threads. When there still can be just one thread. You can just think about it as threads, this kind of design pattern thing. And then generators, async await, which is quite complicated. And then you can have call CC, which is kind of the most fundamental way to do coroutines. There are some caveats, obviously. One caveat is that you might get stack traces. Stack traces can be mangled because, with example, from async await, your function which you call in can be finished by some other thread. So you might get unexpected stack trace, or your environment has to fix stack traces for you to avoid confusion. Another thing is debugging. When you in normal debugger, when you step one line to another, you kind of don't expect that the next line will happen sometime later when another service replies to you. So it's not obvious, and again, it needs some debugging support from environment, I guess. And another thing is thread safety. The reason I mention is that because each line can be potentially executed by another thread, then if you have some shared mutable data between 2 lines, it might not be obvious. But on the other hand, it's pretty much all coroutines, they're available from all these languages, so if you're using one of them, you can use them. And also I should add, in the near future, C++ and Java also come into this. So you can find all the links and all the code here. So thank you for watching. So if there are no questions, I guess we can finish early. I think that there are a couple. So why did the composite synchronous example take 7 seconds and not 5? Just that I can jump into it really fast. I guess it was this next one, right? It was this. It's because we call in C, right? And this is overall promise. And it waits for, inside C, we wait for dog, which is 2 seconds, and then pig. So I guess you're right, it wasn't actually 7. It should be 5. I'm not sure what's the best way to measure. Yeah, it should be 5, I think you're right. Thank you. And I think I kind of answered about difference Go-routines or coroutines. Go-routines, there's like switching context by themselves, unlike coroutines. There is also interesting thing how things will be implemented in Java. So as far as I understand, there will be like common abstraction above threads and coroutines. And you could choose based on what are your needs. And it will also automatically switch to non-blocking I/O and so on. So, but it's like a completely different topic. So yeah, thanks.